I'm Dr. Veera, Clinical Professor of Hematology and Blood Transfusion at the Department of Preclinical Sciences at the Medical Faculty in University Tunku Abdul Rahman. And together with me is...
Hi, I'm Dr. Teo Hoon Koon, Assistant Professor at the same department and co-researcher in the current research we are conducting.
What we are looking at is artificial generation of specific types of red cells that can be used in red cell antibody screen test panels. Now, this antibody screen test is often used to identify patients who may need special types of red cells because they have atypical red cell antibodies that can cause reactions when they get our transfused blood. We are attempting to generate these red cells from induced pluripotent stem cells, or IPSc for short.
iPSCs are reprogrammed cells in that mature cells such as blood cells and fat cells can be reverted back to primitive pluripotent state similar to embryonal stem cells. This technique that was first pioneered by Shinya Yamanaka in 2012, and he went on to be awarded with the Nobel Prize in 2018 for his work. In this technique, we introduce a cocktail of transcription factors into the nucleus of a cell and then consequently changes the behavior of the cell and reverts it back into its primitive state. We then can differentiate it into specific cell types that we want by changing the condition in which the cells are grown or cultured.
You may ask why we want to generate red cells from this iPSC instead of just getting it from regular blood donors. The problem is it is difficult to get specific types of blood from blood donors simply because the combination of these special types of red cells are rare, and it is difficult to sustain the production of the antibody screen cells by just depending on blood donors. The driver for this project is really because we see a need for a sustainable, effective, and economical method of obtaining reagent cells for antibody screening tests, especially in this region. Now, red cells express certain antigens which actually determines the types of red cells a person has. Many would be familiar with the ABO type in that certain people are blood group A, B, or O. A and B people express the A or B antigen respectively, while O people have neither A or B antigens. But most would not, however, know it, but there are currently 360 other antigens that can be expressed on red cells, apart from the A and B antigens. Now, these antigens may also show differences in ethnic groups. So, for instance, the antigens Diego A and MIA may be more common among Chinese and Malays, but it is much less common among Indians, and it is virtually absent among whites. Unfortunately, many labs in this region depend on commercially available reagent cells for identifying patients with antibodies for red cell antigens. And these commercial panels tend to be sourced from Western populations who may not be expressing the red cell antigens that are seen here, like Diego A and MIA. So we end up missing patients who may have antibodies to these Asian type antigens. On the other hand, countries also within this region often find it difficult to produce their own antibody screening cells from their own blood donors because it's difficult and expensive to identify suitable special donors who have the combination of antigens on their red cells. Hence, the push for artificially producing these red cells from genetically engineered iPSC cell lines. So far in our project, we have already produced an iPSC line which contains the genes that makes the Diego A antigen, which is seen mainly in Chinese and at a lesser frequency in Malays. We have also differentiated the cells to make red cells and are further fine-tuning to make the red cell differentiation process and its production much more efficient. We are now hoping to extend the project to the next step, where we will genetically engineer the iPSC to express another antigen which is common among Chinese, that is the MIA, and CAL, which is an antigen that is seen among Indians and whites but very rare in Chinese. So in effect, we are hoping to create a novel iPSC that can be used to make red cells that co-express multiple red cell antigens. Such a cell would be very useful as reagent cells in the transfusion laboratory to identify patients who may have antibodies directed against these antigens. thus making the supply of suitable blood for transfusion to these patients much more efficient and safer.
As the iPS cell line allows unlimited production of RBCs owing to its limitless expansion characteristics, diagnostic centers will not require specific donors to donate their blood frequently to produce antibody screening panels. It eliminates the need for constant pool of reagent blood donors, leading to constant availability and sustainability. Moreover, it gives consistency in the panel as the iPS cell line can be propagated indefinitely, whereby donors keep changing from time to time.
We believe that the results of this research into using engineered iPSC lines to create reagent red cells would make a revolutionary change to pre-transfusion diagnostics in the transfusion laboratory and ultimately lead to safer blood transfusion.